So I placed a simple wire over here, a very simple wire with a battery. And let's make sure we all could see the positive side and the negative side of this battery. That's battery positive, and this is battery negative. So I'm not going to talk about what's happening inside the wire, guys. Not going to talk about inside the battery. Only the net effect because of the battery on the wire. I'm going to talk only about that. Okay, so as soon as you make this connection, the first thing that would happen, by the way, all this is all imaginary. We really don't know what happens and all. So based on the observed phenomenon, people give theories. So this is one such theory. So when you connect a battery to a wire, the first thing that happens is an electric field gets established inside the wire. I'm actually giving you the theoretical way that's actually given in your textbooks. All right, yeah. The theoretical way, first thing is the electric field. It gets established inside this wire. So everywhere there will be electric field. So, and in fact, the electric field direction, because of Benjamin Franklin and all, it's in the direction from battery positive to battery negative. That's the direction of electric field. Let's use this green for electric field. So this is the first thing that happens. Not going to draw it anywhere, it's waste of time, but only these three locations. Okay. Now, whenever there is, I want you to remember this sequence of understanding. When you remember the sequence, it's easy to remember. I mean, it's easy to understand, and also when you represent it later on your paper, on your exam, it becomes very easy. Wherever there is a field, there is also a force. Okay, we talk about magnetic field around a bar magnet. Everywhere that field exists because of forces. Every pinpoint location, there are forces. So wherever there is the electric field, there will be an electric force, and let's use the term Fe. Electric force, we call it electric force. And in fact, electric force is in the direction of electric field. So I'm going one step back. Maybe some of you joined a little later, but let's see step by step. When a battery is connected to a wire, the first thing that happens is inside the wire, an electric field gets established, and the direction of that electric field is from battery positive to battery negative. And the next thing, wherever there's a field, there's always forces inside that field. And that force, we are calling it as Fe, electric force, because it's because of the electric field. And that electric force is also in the same direction of the electric field. Now, there are lots of charged particles inside this wire. Okay, inside this wire, there are a lot of electrons, the charged particles. And what electric field can do is, if the movable charges are positive charges, then it will push in the same direction. Once again, listen carefully. If the charges, please remember the word if. I'm trying to stress on that. If the charges under consideration are positive charges, then the charges will move in the direction of this electric force. But if the charges are negative charges, they will move in the opposite direction of the electric force. So we already know that all the things that are inside these wires are all electrons, which are negative charges. So all these are electrons. These black things I'm using as electrons. And what happens is, because of this electric force, they start to move in the opposite direction. As we just defined, electric field will be there. It has a particular direction. Electric force also has the same direction. If positive charges exist in that material, then those positive charges will move in the direction of this force. Those positive charges will move in this direction. But if there are negative charges like electrons, they will move in the direction opposite. In fact, they will accelerate. Acceleration means, I mean, obviously, wherever there's a force, there's an acceleration. Newton's second law, if you remember, F is equal to ma. Okay, wherever there's a force, there's an acceleration, and all these electrons are accelerating in the reverse direction. Okay, and everything, all of this is happening only because this battery has established a potential difference at the two corners. Okay, at the positive, I mean the wire corner on this side and the wire corner close to the negative side. At these 2 points, a potential difference was established. This corner we can call as high potential region. High potential means, let's say, imagine this is 2 volts battery. Let's call it 5 volts, our wish. So this is a 5 volt high potential, and this can be 0 volt low potential. Some people prefer it like this. They can place it as plus 2.5 and minus 2.5. Even that is okay, guys. High potential and low potential, even that is also fine. Okay, anything is fine. To simplify, I'm using plus 5 and 0. So this plus 5 and 0, the difference between those two potential is 5. So with that 5 volts of potential difference, all these things are happening. Electric field, electric force, then acceleration of electrons. Everything is happening because of that. Okay, let's move further. Now, you already observed this. And in fact, let's imagine, I want to say the length of this wire from this location. That's not a straight line, I know, but please bear with me. Let's say the length of this wire is L. Okay, just this top wire, guys, not the whole copper wire, just this top wire. And we are focusing only on electrons moving from one corner to this corner, from the right side to the left, only along this. So we have a force. Okay, so this is force. We have a displacement of these electrons. Now, if you remember the definition of work done is nothing but force into displacement. So work done is Fe into L. Okay, work done is force into displacement, and this is the overall. I mean, let's imagine there are 1,000 electrons. So whatever work we are speaking over here, this work done that we are speaking about the amount of work done on all the 1,000 electrons in this wire. But if I speak about a single electron, then what I have to do is I have to divide work done with charge of that single particle. So work done per charge, okay, W by Q, this is nothing but the potential or potential difference. So we just defined the theoretical way in the textbook. So whenever there is an electric field, there will be a force. Force will cause electrons to accelerate. And since electrons are accelerating, on electrons, some sort of work is done. That is the work done to move those electrons. And the definition of work is force into displacement. This is the force, and L is the length of the conductor. And when you divide it by a particular charge, we get the potential difference, guys. Okay. So that's everything related to theory. But I want you to know one more thing before we move on to the practical aspect. I want you to know the practical aspect of this also. The thing is about positive work and negative work. Even in 9th class, you have this work, energy, and all that, right? We talk about positive work when, let's say, this is a particle and this is the force. Because of force, the particle is moving in the same direction. Force direction and particle direction are in the same direction. Then we call it as positive work. So if there were positive charges in this wire, it would have been positive work. But what's happening in this experiment or in this discussion, force direction is like this, but electrons are moving in the opposite direction. When the force is resulting in a reverse direction movement, we call it as negative work. So whatever work done in wires, all that is negative work done. Okay. So that's about potential difference, theoretical aspect. And if you observe this formula, we can define potential difference theoretically. It is the amount of work done, guys. Look at the numerator. It is the amount of work done on a unit charge to move it through a particular distance, L. Okay. Or it is the difference in potential between 2 points. Between 2 points, the difference is called the potential difference. Okay? Now,